In this video, I aim to derive a unitary operator in quantum mechanics for a finite rotation about the y-axis. The method will be quite general and can be used to derive operators for the x and z axes as well. We wish to take a wave function, psi, as a function of the position r, to some new wave function, psi primed, as a function r, which is equal to the original wave function as acted on by an infinitesimal rotation operator about the y-axis. This rotation operator acts on the original wave function to take us to the transformed wave function. Note that to begin with, we're going to create an infinitesimal rotation operator about the y-axis for very small rotations delta theta. This allows us to use the small angle formulae, which makes the mathematics much easier. We can then from that derive a finite operator. Firstly, we note that we can use a rotation matrix acting on the wave function to rotate the position vector. If we say Ry is equal to the rotation matrix for rotations about the y-axis, we have Ry is equal to cos theta, 0, sine theta, 0, 1, 0, minus sine theta, 0, cos theta. For a small rotation by delta theta, we can use the small angle formulae. Cos theta is approximately equal to 1, and sine theta is approximately equal to theta, which gives us 1, 0, delta theta, 0, 1, 0, minus delta theta, 0, 1. We can write this in terms of the identity operator and the matrices Si, where in this case S2 is equal to 0, 0, minus 1, 0, 0, 0, 1, 0, 0. And in this case, this gives us Ry of delta theta is equal to the identity operator, subtract S2 delta theta. Plugging this into our original wave function, where we have psi of r going to Ry delta theta on psi r, we can bring the operator inside of the brackets by considering active and passive transformations. This allows us to write the wave function as psi of the inverse operator, Ry inverse delta theta, acting on the position vector. In the case of rotation matrices, because a rotation by theta clockwise is the same as a rotation minus theta anti-clockwise, which is the inverse operation, we can simply write Ry to the minus 1 delta theta is equal to Ry of minus delta theta, which gives us psi of Ry delta theta acting on r. And we know the form of Ry, so we can write psi of r plus S2 delta theta r. This should be a minus sign here, hence the plus in the bracket. Since the angle is small, we're able to perform a Taylor expansion to first order, which will give us psi r, if we expand about r, plus S2 delta theta r dot del psi of r, where we're taking this operation in 3D. Now we wish to explore what S2 delta theta r dot del is. Well, neglecting the delta theta at the moment, we can write this out as some matrix operations. S2 on r gives us 0, 0, minus 1, 0, 0, 0, 1, 0, 0, acting on the position vector x, y, z. In this case, position vector is the operator. This gives us the vector minus z hat 0 x hat. We can then perform the operation minus z hat 0 x hat on d by dx, d by dy, d by dz, which gives us x hat d by dz minus z hat d by dy. What we notice here is that this is very similar to the form of the angular momentum operator ly hat, which is equal to z hat p x hat minus x hat p z hat, where p I hat, the momentum operator, is equal to minus ih bar d by dxi, where xi is equal to x, y, z. This means that we can rearrange our expression for S2 r dot del as firstly minus z hat d by dy minus x hat d by dz. If we multiply the inside of the bracket by ih bar and divide by ih bar outside, we would get minus 1 over ih bar z hat d by dy minus ih bar x hat d by dz. And I'm realizing we probably didn't need to do this negative sign in the first instance, because if we multiply through by minus 1, we would get 1 over ih bar ly hat. And this is a very good expression because it shows that the angular momentum operator Ly hat for rotations is the generator of rotations about the y-axis, which makes sense logically because if you consider giving your system some angular momentum, it would rotate. This allows us to substitute back into Ry delta theta, which will be equal to I minus I over h bar delta theta Ly hat, where we have used 1 over I is equal to minus I. Now we want to explore the construction of an operator u beta for finite rotations theta about the y-axis. Sorry, we will just label this as u beta for now, of finite rotations beta about the y-axis. As before, we'll have some original state psi of r, which we transform to psi primed of r, which is equal to psi of r primed, which is equal to our operator u beta acting on psi of r. What we can consider is splitting our rotation beta into infinitesimal steps. If we divide beta through by n and set n tending to infinity, then our rotation will be sufficiently small to use the rotation operator we just defined, i.e. beta over n equals to delta theta. If we perform this operation an infinite number of times, then we will recover the full finite rotation beta, i.e. we're taking the limit as n tends to infinity of the wave function, where we're going to operate on the position factor r and rotate it by minus beta over n an infinite number of times. So just to recall, the negative sign comes from the fact that ry to the minus 1 of x is equal to ry of minus x. We have beta over n is sufficiently small that we can use ry, and because we sum infinitely through to n, we recover the full rotation beta. Expanding out the inside of the brackets gives us the limit as n tends to infinity, psi of, and letting the operator ry hat act on r, using our expression ry of delta theta earlier, we have r minus the sum from n equals 1 to n, beta over n, s2 r. We can also write this as the limit of, as n tends to infinity, psi of r minus the sum from n equals 1 to n minus 1 of beta over n s2r minus beta over n s2r. This extra component here is the same as if r of beta over n had acted on the wave function psi of r minus the sum from n equals 1 to n minus 1 of beta over n s2r. Therefore, we can write this as the lim, as n tends to infinity, of the operator ry, which is I minus I over h bar beta over n ly hat, psi of r minus the sum from n equals 1 to n beta over n s2r. If we perform this operation n times, then we will get the limit as n tends to infinity, I minus I over h bar beta over n ly hat to the n psi of r. We can now use the identity e to the x is equal to the limit as n tends to infinity, 1 plus x over n to the n. We can see here that x is equal to minus I over h bar beta ly hat. Thus, we can write this as e to the minus I over h bar beta ly hat acting on the wave function psi r. This is the exact same form as our predefined operator u beta that we wanted to find earlier, and so we can say that u beta is equal to e to the minus I over h bar beta ly hat. We also know that u beta is unitary because u beta dagger is equal to e to the minus I over h bar beta ly hat, e to the I over h bar beta ly hat, which is simply equal to 1. So u beta dagger is equal to 1, therefore it's unitary. And I will box our operator here. It should be noted that this unitary rotation operator for finite rotations about the y-axis only holds for spinless particles, and if we want to introduce spin, we have to consider the total angular momentum, J is equal to L plus S, where L is the orbital angular momentum, as has been our sole consideration so far. In this case, u beta for a particle with spin would simply equal to minus e to the minus I over h bar beta jy hat. which can now be applied to particles with spin. This is a topic I've revised a few times now, but given it's quite long-winded and there are significant jumps in mathematics and algebra, I thought it useful to make a video about.